Okay, this video is for Math 140. This is lesson 13.1, the basics of probability theory. So we're just starting this unit and it's all going to be about probability. So today we're looking at calculating the probabilities by counting outcomes in a sample space. Use counting formulas to compute probabilities and understand the relationship between probability and odds. Okay, so on your notes we have sample space and events. Random phenomena are occurrences that vary from day to day and case to case. Although we never know exactly how a random phenomenon will turn out, we can often calculate a number called a probability, that it will occur in a certain way. Like, what are the chances it might rain? Okay, so definitions. An experiment is any observation of a random phenomenon. The different possible results of the experiment are called outcomes. The set of all possible outcomes for an experiment is called a sample space. So we did a lot of this looking at the sample space. What are the possible outcomes in chapter 12? Okay, so let's look at example 1. Determine a sample space for the experiment of selecting an iPhone from a production line and determining whether it is defective. Okay, well, you have two choices. It's either defective or it's non-defective. So those are our two possible events. Okay, so that would be, you have two different things that we could get for that sample space. Okay, let's look at this next one for example 2. 3 children are born to a family and we note the birth order with respect to gender. Okay, so these are the different possibilities. We might have a boy first. Then the second one could be a boy or a girl. Then the third one could be a boy or a girl. So again, this goes back to chapter 12 when we were making our trees. Okay, or we could get boy, girl, girl, and so forth. So if we count the ends, we see here that we have 8 different possibilities. And there they are listed out with the letters B for boy, G for girl. Okay, determine the sample space for this experiment. It says we roll 2 dice and observe the pair of numbers showing on the top faces. So we've seen this one several times. If we roll 2 dice, then these are all your different possibilities. Okay, so we can go 1, 1, 1, 2, 1, 3, and so forth through all of these. So if we count these up, we see that there are 36 different possibilities. Okay, definition. In probability theory, an event is a subset of the sample space. Okay, so like for on that last example, like how many different ways can we roll 12? There was only one sum on the dice that adds up to 12, so 1 out of 36. Okay, so an event, we're going to look for specific thing within that sample space. So we'll write each event as a subset of the sample space. So first we're going to look at a head occurs when we flip a single coin. Then we're going to look at 2 girls and 1 boy are born to a family. And then a sum of 5 occurs on a pair of dice. So let's see if we can figure this out. So for the first one, to get a head when we flip 1 coin, well, getting a head is an event. Okay, so there is one way to get a head. For 2 girls and 1 boy, if we look back at our 8 choices, we could either have a boy first, have a boy second, or have a boy third, and then the others would be girls. So there's 3 different ways for that event to occur. And then to get a sum of 5 on a pair of dice, you can have 1 and 4, 2 and 3, 3 and 2, or 4 and 1. So we have 4 different ways that that event can occur. So here's another definition. The probability of an outcome in a sample space is a number between 0 and 1 inclusive. So like if it was there's nothing, of course we can get 0. So if there's none in there, so like if I was trying to get a sum of 13 on the dice, that does not ever add up to 13, so you'd have 0 possibilities. Or it could be the whole entire group, right? And that would equal 1. So if you had 36 out of 36, that would total to 1. So that's what that means by inclusive. The sum of the probabilities of all the outcomes in the sample space must be 1. So like if you add all the probabilities together, it has to add up to 1. The probability of an event, written as P for probability, E for event, okay, so you'll see it written like this, is defined as the sum of the probabilities of the outcomes that make up E. So let's look at how we look at this. Okay, we also have, this is another way to look at P of E. So if E is an event and we perform an experiment several times, then we estimate the probability of E as follows. The number of times E occurs, so like if we were spinning a spinner, how many times do we land on 5? And the bottom number would be the number of times the experiment is performed. So like if we were spinning a spinner and we got 5 5s and we spun it 30 times, okay, then we'd have 5 over 30, which always simplify your fractions. Okay, we would have 1 out of 6. So that would be called your relative frequency. So you make it into a fraction and simplify it. So always simplify your fractions. Okay, so let's look at some examples here. So this is example 5 on the back side of the first page of your notes. So it says a pharmaceutical company is testing a new drug. The company injected 100 patients. And so then here are the results. So we have side effects, none. 72 of the people had no side effects. Okay, for mild side effects, we had 25. And so for severe, we had 3. So it says, if a person is injected with this drug, what is the probability that the patient will develop severe side effects? Well, of course, we tested 100 people. So only 3 of them had severe side effects. So we're going to take the number of times the severe side effects occurred over the number of times the experiment was performed. So that gives us 3 out of 100. Okay, which if we change it to a decimal, we get 0.03. That is definitely between 0 and 1. Okay, so that works. That would be our number or probability of getting our severe side effects. Okay, let's look at another one here. So this table summarizes the marital status of men and women in thousands. So each of those numbers is thousands. In the United States in 2006, if we randomly pick a male, what is the probability that he is divorced? Okay, well, we're looking at, we'd have to add all of those up, okay, and then look at how many are actually divorced. Okay, so notice how they're adding all of the ones highlighted in pink there together. So we get, in total, we have 116,326, and again, this is in thousands. And then how many are divorced? Is that 10,818. So again, we make it into a fraction, and we divide that, we get 0.093 would be our probability. If you wanted to change that to percent, of course, we would just move the decimal over 2 places. So about 9.3% likely that if you choose a male randomly, that he's been divorced. Okay, counting and probability. Probabilities may be based on empirical information or the result of experimental data. So probabilities may be based on theoretical information, namely combination formulas. So let's look at these. So we talked about these also in chapter 12. We flipped 3 fair coins. What is the probability of each outcome in this sample space? We know each time we flip a coin, we can get heads or tails. Okay, and since we are doing 3 coins, here's our different possibilities. All 3 heads, 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 tails, heads, tails, heads, heads, tails, tails, and then we have our tails, heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. Okay, so again, remember 3 coins, that's the same as taking 2 to the 3rd power, which is 8. And you'll notice if you count those up, we have 8 different possibilities. So that would be our sample space. So again, you could use your fundamental counting principle, 2 times 2 times 2, or 2 to the 3rd power is 8 to get your sample space. So each of these outcomes are just as likely, so each has a probability of 1 in 8. Okay, we draw a 5-card hand from a standard 52-card deck. What is the probability that we draw one particular hand? Okay, well first, how many hands are possible? So think about what we learned in chapter 12. You can find this by doing a combination, right? Because the order doesn't matter, so we're going to use a combination. So if we take a combination, 52 things, where we're choosing 5 of them, we get 2,598,960 different possible hands. So if you want one particular hand, okay, then you have 1 chance in all of those of getting a particular hand. Calculating probability when outcomes are equally likely. So if E is an event in a sample space S with all equally likely outcomes, so for instance, flipping the coins, then the probability of E is given by the formula. So the number of E and the number of your sample space. So some good advice. If the outcomes in a sample space are not equally likely, then you cannot use this formula. So like for instance, if we had a spinner and each of the pieces were not equal sized, then like if we have one that's like half of the spinner and the other 3 are only 1/3 of the spinner, okay, we can't use this formula because we can't get each piece equally likely. They would all have to be the same size. What is the probability in a family with 3 children that 2 of the children are girls? So think about our previous example when we were going through and saying one of them was a boy, right? Okay, because in order to get 2 girls, then you'd have to have 1 boy. Okay, we know that there are 8 outcomes in this sample space that we saw from example 2. Okay, for the event that 2 of the children are girls, there was 3 outcomes. Okay, you could have the boy first, the boy in the middle, or the boy last. And so to find the probability, we're going to take the probability of getting G, which is 3, over our number in the sample space, which was 8. So 3 out of 8. What is the probability the total of 4 shows when we roll 2 fair dice? Remember, there's 36 total dice, or numbers possible on our dice. So in order to get a total of 4, we can get a 1 and a 3, a 2 and a 2, or a 3 and a 1. So there's 3 different ways that we can add up to 4 on those dice. So if we make that into a fraction, 3 out of 36, remember to always simplify, simplifies to 1/12. So you can always just get in the habit of plugging it in as a fraction in your calculator, and your calculator can simplify it for you. Okay, then if we draw a 5-card hand from the 52-card deck, what is the probability that all 5 cards are hearts? So first, we already did this sample to find the sample space. We did 52 cards and we chose 5 of them. Remember that came up to be like our 2 million, big number. And then if you only want to draw hearts, then there's only 13 hearts in the deck. So out of the 13 hearts, then we're going to just choose 5. So that's going to be our numerator. Okay, so that comes up to be 1,287 over that 2,598,960. If you were to divide that and get a decimal, you're talking about 0.000495. Okay, even if we change that to a percent, it's less than 1%, right? This is 0.0495%. Okay, so not very good odds of getting 5 cards that are all the same hearts, because it wouldn't matter if we did spades or diamonds, you would come up with the same probability. Okay, on example 12, 4 friends belong to a 10-member club. 2 members of the club will be chosen to attend a conference. What is the probability that 2 of the 4 friends will be selected? Okay, so you think about our sample space. Okay, you have the possibility of choosing 2 members out of the 10. Okay, so if we do a combination, remember this is what your calculator is doing. Okay, we'll just spit out the 45. There's 45 different ways that we can choose 2 people out of the 10 members in the club. So to see if you're going to choose 2 of the 4 friends, well, we have 4 people, and if we're going to choose 2 of them, there's 6 different ways we can choose 2 of them. So now we're just going to make our fraction 6 over 45 and simplify that. So 2 out of 15 ways, when you simplify it, can we get 2 of the 4 friends will be selected? Okay, for this next one, you may want to pause this video and then go to the second link that I posted for the genetics. So you can watch that and then come back and finish this video at this point. Okay, so you watched that little video clip. Hopefully it worked for you for about the probability and genetics there. So if we are looking at Y produces yellow seeds, that's the dominant gene, and G produces green seeds is your recessive gene. Okay, so if you have a parent with a YY and a parent with a GG, okay, then in the first generation, we get YG, YG, YG. They all end up to be yellow because that's the dominant gene. Okay, crossing 2 first-generation plants. So now if we take 2 first-generation plants and we cross them, okay, we get the possibility of getting a YY, which would mean definitely yellow, or a YG, or a GY, which would still be yellow, or there is a chance of getting GG. Okay, so there is a chance of getting a green then. Okay, so this is taking 2 first generations, and these are our possibilities. We'd get 3/4 of them should end up to be yellow, but 1/4 would end up to be green. Okay, so they use thinking like this to help us determine about other genetic diseases that might be passed on through heredity. So this one's looking at sickle cell anemia. It's a serious inherited disease. A person with 2 sickle cell genes will have the disease, but a person with only 1 sickle cell gene will be a carrier. So it means they could pass it on to their children. So if they married somebody who was a carrier, there is a possibility that their child could have this disease. So the table below shows both parents as carriers. Okay, so they've each got 1 gene. Okay, so SS, you both have both, they have the disease. Okay, these children, if you have SN or NS, then you're just carriers. And if you're NN, then you're normal. So that child would not be able to pass it on to any of their children if they're NN. Okay, the child has sickle cell anemia. So we have 4 different possibilities. Only one of them ends up with sickle cell anemia. So that's 1 in 4 chances. The child is a carrier. We see that you have 2 possibilities out of the 4. So 2 out of 4 simplifies to 1/2. The child is disease-free. Well, we see that there's only one way to end up with disease-free. So that would be 1 out of 4. Okay, our last section here is on odds. If the outcomes of a sample space are equally likely, then the odds against an event E are simply the number of outcomes that are against E compared with the number of outcomes in favor of E occurring. We would write these odds as, remember that little line means not. Okay, so that's the E to the not is the complement of the event. Okay, so what's the odds of it not happening against the odds of it happening? Okay, so if a family has 3 children, what are the odds against all 3 children being of the same gender? What are the odds in favor? Okay, well, let's see. Okay, these were our 8 different ways that those children could be born. So against, there are 6 different ways that they could not be all the same gender, and only 2 ways that they could be in favor. So for the first one, we have 6 to 2, which again, these can simplify just like fractions, or we have a 3 and 1, that the children are going to be of the same gender. And the odds in favor, okay, so odds in favor, you have 2 out of 6, which simplifies to 1 in 3. So I have a 1 in 3 chance that they would all be of the same gender. Okay, a roulette wheel. So remember, this is a wheel that you spin, and it has the 38 different numbers, usually colored red and black. Okay, and 36 of the compartments are numbered with 1 to 36. The remaining 2 compartments are green and numbered with a 0 and a 00. A small ball is placed on the spinning wheel and ends up in one of the compartments. What are the odds against the ball landing on red? We got to think about all of the ways that you cannot get red. Okay, you got 38 equally likely outcomes. Okay, 18 are in favor and 20 are against the event landing on red. Okay, so what are the odds against? That's where we would take our 20 to 18, and of course you can write as a fraction too. There's different ways you can write odds. We can write it with the 2, the colon, or even as a fraction. And if we simplified that, okay, it reduces to 10 to 9. Okay, so these are the odds against it. So we have a 10 to 9 chance against getting a landing on red. Okay, if E naught is the complement of the event, then the odds against E, you would take the probability of not getting E over the probability of getting E. Again, we're not doing the total here. This is not using sample space like we were for the others. So if the probability of E is 0.3, then the odds against E would just be subtracting it. Okay, so if we did against E, we would do 1 minus the 0.3 gives us the 0.7. Okay, over the probability of E, so not E over E, and we would simplify that. Okay, which we could write it as 70-30 or 7 to 3. Okay, would be our odds against E. We have a 7 to 3 odds against E. Okay, so let's look at this one. If the probability of Green Bay winning the Super Bowl is 0.35, what are the odds against Green Bay winning the Super Bowl? So remember, we got to find against. So if this is for winning the Super Bowl, against we would subtract it from 1, okay, which gives us the 0.65. Okay, and then we'd say that to your probability for doing it is your 0.35. Okay, if you type this right here on the Casio calculator will actually do this math for you and simplify it. Okay, some other calculators give you an error message if you put decimals in your fractions, but the Casio can simplify that for you to give you the 13 to 7. So that would be your odds. You have a 13 to 7 odds against Green Bay winning the Super Bowl. Okay, so now you can work on your homework 13.1 on Math Excel.